Good evening, dear students. So we have come to an last bit of discussing nanomaterials and their applications. So in this applications, method of application, before coming to the discussion one by one, the carbon nanotubes we'll discuss. What are carbon nanotubes? Now these carbon nanotubes are either single-walled carbon nanotubes or multi-walled carbon nanotubes. Now the carbon nanotubes are allotropes of carbon with cylindrical nanostructures. And the carbon, the hexagonal carbon with all the carbon atoms are which is sp2 hybridized configurationally equivalent to a graphite sheet, which is once these graphite sheets are rolled into the form of a cylinder. Now, when you take a single sheet and roll into the form of a cylinder, you get a single-walled carbon nanotubes. That is called a single-walled. If you take a multiple sheets of these hexagonal layers of graphite and roll into the form of a cylinders, and you get a multi-walled carbon nanotubes. Now the synthesis can be achieved by the first method is arc discharge, and the second method is the laser ablation. These are the familiar methods of synthesis, and the third one is chemical vapor deposition. So three methods are usually employed, and that is arc discharge, laser ablation, as well as chemical vapor deposition. Now, this is the typical structure of scanning electron microscopic images of carbon nanotubes. So you can very some images. It's very clear the formation of the tubular structures of a rolled graphite sheet. So this is the again the FESM, the scanning electron microscopic structure of a hexagonal ring structure of a carbon, which is rolled into the form of a typical cylinders. Now, these what are the properties of carbon nanotubes? The properties of carbon nanotubes includes show a unique combination of stiffness. So once these hexagonal graphite sheet is rolled into the form of cylinders, and the stiffness or the strength of the tenacity increases as compared with the other fiber materials, which usually lack one or more of these properties. And they also exhibit high thermal and electrical conductivity. So the first property is that the strength or the stiffness or the tenacity increases, and they exhibit high thermal and electrical conductivity as compared to the other conducting materials. And their final usage, however, may be limited to their potential toxicity. Now, as I said in the previous, if the single sheet of graphite is rolled into the form of cylinders, so the graphite is rolled into the form of cylinders. If the single sheet is taken, that is what you get in SWCNTS, that is single-walled carbon nanotubes. If the multiple sheets are taken and rolled into the form of cylinders, and they are called as multi-walled carbon nanotubes. So you get two varieties here. One is single-walled carbon nanotubes, as well as the second one is multi-walled carbon nanotubes. And these carbon nanotubes applications, the first application is carbon nanotubes are extensively used for the conducting plastics. So conductive plastics which are made up of carbon nanotubes. And the second one is structural composite materials. So the third one is biosensors for harmful gases. So different harmful gases detection biosensors are made up of doped carbon nanotubes. Now the fourth one is micro and nano electronics, and the fifth one is batteries with improved life. And the second compound is fullerenes. Now the fullerenes are the allotropic form of carbon, and these fullerenes will exist in the form of a three-dimensional allotropic structures with the carbon or carbon in graphite. It's like a diamond-shaped structure. Now they possess a carbon case-like structures, carbon with a case-like structures, and composed of honeycomb type lattice hexagons and pentagons. So the fullerenes are made up of the case type structures with honeycomb type lattices of hexagons as well as pentagons, and these fullerenes is available in the form of a tube. So the available in the form of a tube, or maybe an ellipsoid, or maybe hollow spheres. So the fullerenes, essentially, it is a cased honeycomb type of structures of carbon, either maybe in a hexagonal ring or maybe a pentagonal ring. So the mixture of the hexagonal ring and pentagonal ring fused and formed into an shape of honeycomb type. Now the cylindrical fullerenes are also known as carbon nanotubes, and the spherical ones are also called as buckyballs because they resembles the famous architecture of Buckminster Fuller. Now the architect of our Buckminster Fuller designed a geodesic dome for the 1967 and a Montreal World Exhibition with the same structure like this. So the two-dimensional and three-dimensional fullerenes. Now, when you look into the properties of the fullerenes, now the properties of the fullerenes are mainly the first property of the fullerenes is a typical fullerenes are made up of 26-membered ring and 12 5-membered ring. So typically, a typical fullerene consists of 26-membered carbon hexagonal ring and 12 5-membered pentagonal ring. Now, each 6-membered ring can fuse with either 6 or 5-membered ring. Now, the 6-membered ring you can see from the figure is can fuse with either 6-membered ring or maybe a 5-membered ring. So, 6-membered ring can fuse with either 6-membered ring or 5-membered ring. Now, all the carbon atoms. Now, the one carbon is connected to 3 other carbon atoms. Now, all the carbon atoms are sp2 hybridized, and if there is once the sp2 hybridization forms, there is a formation of pi electrons, and these unhybridized pz pi electrons will delocalize over the ring system. Now, the carbon atoms occupies the vertices, and once you look into the vertices and the symmetric operations, almost 120 symmetric operations are possible in typical fullerenes. Now, the carbon atoms containing C60, C70, C76, C78, and C84s are widely studied. So, these carbon atoms containing fullerenes are widely studied. Now, the synthesis. Synthesis is a typical synthetic procedure. In this typical synthetic procedure, and the first one is the electric arc discharge. Electric arc discharge is the familiar synthetic procedure for the synthesis of fullerene. And the second one is the laser ablation. And third one is chemical vapor deposition. Now the properties, as I said, it contains a 26-member ring and 12 5-member ring. All the carbon atoms are sp2 hybridized, and the unhybridized pre-jet electron will delocalize over the ring systems. And due to this delocalization of unhybridized pre-jet electron, the fullerenes will show a semiconducting nature. And it is quite stable from chemical and physical points of view. There is very stability, high stability, and breaking the balls requires a temperature of almost 1000 degrees Celsius. So up to 1000 degrees Celsius, the fullerenes are quite stable. Now, because of this, the formation of a case rings type of structures, it exists as a highest tensile strength in the 2D structure of the element. The highest packing efficiency, highest packing density of all known structures. Now the applications are widely used. Fullerenes are widely used as molecular sensors for detection of organic molecules. Television screens and bookie papers may be more efficient than CRT and LCD displays. and has the potential to carry a drug in the interior of the own molecules and release the drug once the buckyball reaches a certain cell or the tissue within the body. So it is used in medical therapy, and these fullerenes may be doped with metal ions inside, maybe in the organic solar cells, in the production of high efficient organic solar cells, and become a crucial parts in the nanoelectronic devices. So the fullerenes are widely used in material electronics, nanoelectronics, the development of organic based solar cells, and when compressed to 70% of its original size, these buckyballs becomes more and more hard and as like the diamond. Applications of nanomaterials-based products: one is automotive industry and engineering, medicine, cosmetics, textile, sports, chemical industry, and electronic industries. Now the last one, last molecule, which is the graphenes. Now you know very well, graphene is a six-membered hexagonal carbon structures. It's an allotrope of a carbon. Once you look into the properties, it's an allotrope of a carbon with a single layer of arrangement of carbon atoms in the hexagonal lattice. And it is also called as a zero band gap materials because band gap is almost zero between the conduction and valence band in case of the graphenes. Now it is a very crystalline allotropic form of carbon with resembling 2D properties of carbon and has a four bonds. One is a sigma bond, and each of the three carbon neighbors and unhybridized pz pi electrons will delocalize over the ring system. Now it is all the carbon atoms are sp2 hybridized and gives more stability. So you know very well that sp2 hybridized carbon atoms is more stable, and the bond distance is almost 1.42 angstrom units. So the bond distance is 1.42 angstrom units. The carbon atoms are sp2 hybridized, and the pz orbital undergoes hybridizations to form a p pi and p pi star orbitals. So you have two orbitals of pz electrons. One is p pi as well as another is p pi star orbitals, and these delocalized bonds are responsible for electronic conductivity in the graphene molecule. And these carbon nanotubes applications, the first application is carbon nanotubes are extensively used for the conducting plastics. So conductive plastics which are made up of carbon nanotubes. And the second one is structural composite materials. So the third one is biosensors for harmful gases. So different harmful gases detection biosensors are made up of doped carbon nanotubes. Now the fourth one is micro and nanoelectronics, and the fifth one is batteries with improved life. Thank you.